Continuity, continuous functions, epsilon-delta proofs. In this section, we define what a continuous function is and prove basic relations between continuous functions and arithmetic operations. We conclude this section by proving that all rational functions are continuous on their domains. Let f be a function defined on some open interval I, and let a be in I. A function f is continuous at a number a if for every epsilon greater than 0 there exists a delta greater than 0, such that for all x in I we have this. We note that the open intervals that we consider can also be unbounded, that is, can have the forms here. In terms of limits, for a function f and a number a from the definition, the fact that f is continuous at a number a can be restated as the equality here. Let f be a function defined on some open interval I. A function f is continuous on an interval I if it is continuous at every number a in I. Let fg such that I is onto R, where I is a subset of R, is an open interval. If f and g are continuous at a in I, and c is a constant, then the following functions are also continuous at a. Let epsilon greater than 0 be arbitrary. By the definition of continuity, there exists delta 1, delta 2 greater than 0, such that for all x in I, we have this. Set delta equal minimum delta 1, delta 2, then for all x in I, such that x minus a absolute value less than delta, we have that this, and consequently this. This proves that f plus g is continuous at a. Let epsilon be greater than 0 be arbitrary. By the definition of continuity, there exists delta greater than 0, such that for all x in I, we have this. Then, for all x in I, such that x minus a absolute value less than delta, we have this. Since this, therefore, CF is continuous at A. By part 2, we have that the function negative g is also continuous at A. The conclusion now follows from part 1 by noting that f minus g can be written as a sum f plus minus g. Let epsilon be greater than 0 be arbitrary. By the definition of continuity, there exists delta 1, delta 2 greater than 0, such that for all x in I, we have this and this. Set delta equal minimum of delta 1, delta 2, then for all x in I, such that x minus a is less than delta, we have this and that. These inequalities further imply that this and that. This shows that fg is continuous at a. Assume that g of a does not equal 0. By the definition of continuity, for epsilon 1 such that this, there exists delta 1 greater than 0, such that for all x in I, this. Thus, for all x in I, such that x minus a absolute value less than delta 1, we have this. This shows that g of x does not equal 0 for all x in I, such that x minus a absolute value less than delta 1, and therefore f divided by g is well defined in the neighborhood of a. Let epsilon greater than 0 be arbitrary. Once again, by the definition of continuity, there exists delta 2, delta 3 greater than 0, such that for all x in I, this and that. Set delta equal minimum of delta 1, delta 2, delta 3. Then, for all x in I, such that x minus a absolute value less than delta, we have that this and that. From here, it follows that equalities and inequalities, we conclude that f divided by g is continuous at a. Using the induction principle, note that the parts 1 and 4 of the previous theorem can be extended to any finite set of functions. More precisely, if the functions are continuous at a, then the addition of functions and multiplication of functions are also continuous at a. A function p of x here, where this is called a polynomial. The domain of a polynomial is R. If d is the largest index such that ad does not equal 0, the polynomial p is said to have the degree d in notation this. We recall that a polynomial of degree d can't have more than d zeros. If all equals 0, then p of x equals 0 for all x in R. The degree of such polynomial is not defined. By writing this, it is a practice to assume that an does not equal 0. That is, this. If p and q are polynomials, with q not being a zero polynomial, the ratio p over q is called a rational function. The domain of a rational function, p over q, equals this. This domain is the real line R except a finite set of numbers x for which q of x equals 0. 1. Every polynomial is continuous on R. 2. Let p and q be two polynomials, with q not being a zero polynomial. A rational function p over q is continuous on its domain. Step 1. Let C in R. Let us first show that a constant polynomial, here, is continuous on R. We fix a in R and let epsilon greater than 0 be arbitrary. Then for any delta greater than 0 and any x element of R, we have this. By the definition of continuity, a constant polynomial is continuous on R. Step 2. Next, let us show that a linear polynomial, here, is continuous on R. Again, we fix a in R and let epsilon greater than 0 be arbitrary. Choose delta equal epsilon. Then, for any x in R, we have this. This shows that a linear polynomial is continuous on R. Step 3. Using the induction principle, let us show that polynomials are continuous at an arbitrary point A in R. The case n equals 1 was proven in step 2. Now, assume that the statement is true for n equals k. Then, this is continuous at A as a product of two functions continuous at A. By induction principle, polynomials are continuous at A for all n. Step 4. Let A and R be arbitrary and let p of x be an arbitrary polynomial. Then p of x can be written as this, where that are introduced in step 3. By part 2 of theorem 3.1 and step 3, we have that the polynomials are continuous at A. Finally, using step 1 and part 1 of theorem 3.1, we conclude that p of x is continuous at A. Since A and R was arbitrary, we have that p of x is continuous on R. Thus, we showed that any polynomial is continuous on R. Since any polynomial is continuous on R, part 5 of theorem 3.1 implies that any rational function is continuous on its domain. In this section, we prove several main properties of continuous functions: continuity of composition of functions, intermediate value theorem, continuity of inverse functions. In this section, we assume that the function f is defined on an open interval I, the function g is defined on an open interval j, and f of I is a subset of j. In this case, we can define the composition h of f and g by this. This composition is denoted as h equals g of f. If the function f is continuous at a number a in I, and the function g is continuous at a number b equals f of a in j, then the composition g of f is continuous at a. Let epsilon greater than 0 be arbitrary. Since g is continuous at b in j, there exists gamma greater than 0 such that for all y in j, this. Furthermore, by continuity of f at a and I, for epsilon 1 defined as gamma, there exists delta greater than 0 such that for all x in I, this. Hence, for all x in I, such that x minus a absolute value less than delta, we have that this, where the last inequality holds due to 1, and the fact that this. By definition, g of f is continuous at a. Let f be a continuous function defined on an open interval I subset of R, and let a prime be in I, a less than a prime. Then for every number b that lies between f of a and f of a prime, there exists a number c such that f of c equals b. If b equals f of a, we can take c to be equal to a. If b equals f of a prime, we can take c to be equal to a prime. Hence, let b not equal to f of a and b not equal to f of a prime. Without loss of generality, we assume that f of a less than b less than f of a prime. Let c be defined as this, and let us show that f of c equals b. Since f is continuous and this, there exists delta in this such that for all x in this and all x prime in that. This implies that this. The function f is continuous at c, so for an arbitrary epsilon greater than 0, there exists gamma greater than 0, such that this. By definition of the supremum, there exists x in this, for which f of x less than or equal to b. Furthermore, for any x prime in this, we have f of x prime greater than b. Also, this and that by 2. It now follows that this and that, hence f of c minus b absolute value less than epsilon. Since epsilon greater than 0 is arbitrary, we conclude that f of c equals b. Denote by j the range of f, this. We say that a function f is one-to-one or injective if equality f of x equals f of x prime implies x equals x prime. In this case, we can define the inverse function f inverse in the following way. F inverse of y equals x if and only if y equals f of x. Let f be a continuous and strictly monotone function defined on an open interval I. Then, f is one-to-one, the range j of f is an open interval, the inverse function, f inverse, is continuous on j. Without loss of generality, we may assume that f is strictly increasing. In the case when f is strictly decreasing, consider the function minus f. In other words, this, specifically that. And thus the function f is one-to-one. Note that we haven't used the continuity of f for this part. Consider numbers y, y prime in the range j of f. Assume that y less than y prime. Then there exists x, x prime in I such that f of x equals y, f of x prime equals y prime. We note that x less than x prime since f is strictly increasing. By the intermediate value theorem, for each z in this, there exists omega in this, such that z equals f of omega. Thus, the segment, this, is in the range of f, that is, this. By the characterization theorem for intervals, here, we deduce that j is in an interval. This proves 2. Consider b and j, and let a and I be such that f of a equals b. Let epsilon greater than 0 be arbitrary, but small enough so that this. Denote delta equal this. We note that delta greater than 0 since f is strictly increasing by assumption. Let f minus b absolute value less than delta, then this. By the intermediate value theorem, there exists x in this such that f of x equals y. Since f inverse of y equals x and f inverse of b equals a, and this, we find that this. This proves the continuity of the function f inverse at point b in j. Finally, since b was arbitrarily chosen, we have that f inverse is continuous on j. It is important to mention that we don't discuss the one-sided continuity here. Theorem 8.1 holds also for closed segments when continuity on the ends of the segment is understood as a one-sided continuity. Namely, if f is continuous and strictly monotone, then its range is a closed segment. F is 1 to 1, the inverse function, f inverse, is continuous. In this section, we prove the continuity of elementary functions. In this section, we prove that exponential functions are continuous on R. We start with auxiliary lemmas. For every epsilon greater than 0, there exists n such that for all positive integers n, we have this. Using the binomial theorem, we have that for all positive integers n greater than or equal to 2, we have this. By taking the nth root in the previous inequality and using the monotonicity of the root function, we deduce that for all positive integers n greater than or equal to 2, we have this. Let n equal this, where that denotes the greatest integer less than or equal to x. Then for all positive integers small n, we have this, since that. For any number a greater than 1, and for any epsilon greater than 0, there exists n such that this. By lemma 10.1, there exists n such that for all positive integers small n, we have this. Now, let small n be arbitrary such that n is greater than maximum of big N or a. Then it immediately follows that this. For every positive number a, the exponential function is continuous on R. We consider the cases a equals 1, a greater than 1, and a between 0 and 1 separately. Case a equals 1. In this case, a to the power x equals 1, x element of real numbers, the continuity of this function follows directly from theorem 4.1. Case a greater than 1. Let r in real numbers be an arbitrary but fixed real number, and let epsilon be greater than 0. Set alpha defined as this. Using lemma 10.2, we can choose a positive integer n such that this. Let delta in this, we observe that this, since this and that. Now let x in R be such that x minus R absolute value less than delta. From here, this. It follows from 3 that this, and that, hence this. Multiplying a to r greater than 0, we find that this is less than epsilon. Thus we prove that the exponential function is continuous at r. Since r, element of real numbers, was arbitrary, we conclude that the exponential function is continuous on r. Case a between 0 and 1. The continuity of a to the power x in this case follows from the previous case in part 5 of theorem 3.1. Indeed, a to the x can be written as a to the x equals this, and also 1 over a greater than 1. For every positive number a not equal to 1, the function a to the x is strictly monotone on R and has range this. By the inverse function theorem, there exists an inverse function log base a of y greater than 0, defined by equation a to the log base a of y equals y, logarithmic function. Furthermore, the inverse function theorem now immediately implies the following result. For every positive number a not equal to 1, the logarithmic function log base a of y is continuous on 0 to positive infinity. In this section, we prove that trigonometric functions sine x, cosine x, tangent x, cotangent x are continuous on their domains. In order to prove the continuity of sine x, we first need the following lemma. For all x in R, it holds that absolute value sine x is less than or equal to absolute value x. We consider the following cases. Case absolute value x greater than or equal to pi over 2. In this case, we immediately have this. Case x between 0 and pi over 2. Consider unit circle and let x be an angle AOC. Since the height AH equals sine x and the length OC is equal to 1, the area of triangle OAC equals half sine x. The area of sector OAC equals half x. Comparing areas visually, we find that this and thus that. Case x between negative pi over 2 and 0. This follows from the previous case, since negative x, element of 0 to pi over 2, and this. Case x equals 0. Note that absolute value sine x equals 0 equals absolute value x. The function sine x is continuous on R. Fix a in R and let epsilon greater than 0 be arbitrary, since delta equals epsilon. If absolute value x minus a less than delta, then lemma 13.1 implies that this. From here it follows that these equality and inequality. By definition, the function sine x is continuous at a. Since a in R was arbitrary, we deduce that the sine function is continuous on R. The function cosine x is continuous on R. Note that sine of x plus pi over 2 equals cosine x. So the function cosine x is a composition of continuous functions x plus pi over 2 and sine y. By theorem 6.1, the function cosine x is continuous on R. The function tangent x is defined as tangent x equals sine x divided by cosine x. Its domain consists of all real numbers x for which cosine x does not equal 0. That is, the domain of tangent x is this. Part 5 of theorem 3.1 and the continuity of sine and cosine functions immediately implied the following result. the function tangent x is continuous on its domain. The function cotangent x is defined as cotangent x equals cosine x divided by sine x. Its domain consists of all real numbers x for which sine x does not equal 0. In other words, the domain of cotangent x is this. Part 5 of Theorem 3.1 and the continuity of sine and cosine functions immediately implies the following result. The function cotangent x is continuous on its domain. In this section, we define inverse trigonometric functions, inverse sine, inverse cosine, inverse tangent, inverse cotangent, and prove that they are continuous on their domains. Function sine x is strictly monotone on the segment and has range. By the inverse function theorem, Theorem 8.1, there exists an inverse function defined by relations, the arcsine. Furthermore, the inverse function theorem now immediately implies the following result. The arcsine function is continuous on -1 to 1 non-inclusive. Using the notion of one-sided limit and the remark 8.1, one can deduce that inverse sine of y is continuous on -1 to 1 inclusive. Function cosine is strictly monotone on the segment and has range. By the inverse function theorem, Theorem 8.1, there exists an inverse function, inverse cosine, defined by relations. Furthermore, the inverse function theorem now immediately implies the following result. The arc cosine function is continuous on -1 to 1 not inclusive. Using the notion of one-sided limits and remark 8.1, one can deduce that inverse cosine is continuous on -1 to 1 inclusive. Function tangent x is strictly monotone on the interval and has range. By the inverse function theorem, Theorem 8.1, there exists an inverse function defined by relations. Furthermore, the inverse function theorem now immediately implies the following result. The arctangent function is continuous on R. Function cotangent is strictly monotone on the interval and has range. By the inverse function theorem, Theorem 8.1, there exists an inverse function defined by relations. Furthermore, the inverse function theorem now immediately implies the following result. The arccotangent function is continuous on R. That was continuity, continuous functions, epsilon-delta proofs. Thanks for watching.